You ever just stop and think about how wild the internet is? I mean, really think about it. The idea that you can watch a movie or video call someone clear across the planet, and all of that information is literally traveling to you as pulses of light trapped inside a strand of glass that's thinner than one of your hairs. I mean, it sounds like something out of a sci-fi movie, right? But it's not. It's happening right now, this very second. And we're going to break down exactly how it all works. I mean, it just sounds impossible, doesn't it? How do you cram the entire digital universe, all those cat videos, all those emails, all that data, into these tiny, almost invisible glass threads? Well, that's the big question, and that's exactly what we're going to solve together. And look, we're not just making this up. We're digging into some seriously dense engineering textbooks, like this one, and we're boiling down all the complex science into one simple story. Don't worry, you are not going to need a PhD in physics for this, I promise. So, to really get this, we're going to shrink ourselves down and follow the journey of just one tiny piece of information. Let's imagine it's a single pixel from the video you're watching right this moment. We're going to follow its epic trip all the way to your screen. Okay, so first things first, we have a huge problem to solve. How on earth do you trap a beam of light? I mean, light travels in straight lines. If you shoot it down a glass wire, what's to stop it from just leaking out the sides? Well, the answer starts with something you've seen a million times. It's called refraction. It's just the way light bends when it goes from one thing to another, like from the air into a glass of water. You know how a straw in a glass always looks like it's broken right at the surface? That's refraction. And that little bend is our first big clue. And here is where the magic happens. If you get that light beam to hit the edge, that boundary, at a really, really shallow angle, something incredible happens. The light doesn't bend and escape. No, it reflects perfectly. 100% of it bounces right back inside. This is called total internal reflection, and it is the absolute secret sauce that makes all of fiber optics possible. So here's how they build the cable to make this happen. You have a glass center called the core, and it's wrapped in another layer of glass called the cladding. Our light pulse, carrying our little pixel, gets fired into the core. It travels until it hits the boundary with the cladding at that super shallow angle, and bam, total internal reflection. It bounces perfectly and just keeps on zigzagging its way down the fiber, completely trapped inside. The best way to picture it is to imagine our light pulse is zipping down a perfect, never-ending tunnel made of mirrors. It's flawlessly guided, bouncing from one side to the other at pretty much the speed of light. All right, so we've figured out how to trap the light. That's step one. But our pixel, remember, it starts its life on a server somewhere as electricity. So how do we get from electrons to photons? How do you turn data into light? You know, this is the massive upgrade from those old copper wires. Copper works by literally pushing slow, kind of heavy electrons around. Fiber optics, it uses photons, the actual particles of light. These things have no mass, and they move at the universe's ultimate speed limit. It's a completely different ballgame, a huge leap in technology. So, that big conversion from electricity to light, it all happens inside a tiny little thing called a semiconductor laser. You can think of it as the starting gun for our data's race. It takes the electrical ones and zeros from the computer and converts them into an incredibly focused, pure beam of light. But wait, how does the data get encoded? Well, the laser actually shines a continuous beam. Right after the laser, there's something called an optical modulator, and this thing is basically the fastest light switch you can possibly imagine. It flickers on and off billions of times a second. Every little flash of light is a 1. Every time it's dark, that's a 0. And just like that, you've got a perfect copy of your data, written in light. Okay, our pixel is now officially a pulse of light, zipping through that glass fiber. But you know, sending it across town is one thing. How does it survive a journey of thousands of miles, say, across the bottom of the ocean? And that's the next big hurdle, right? I mean, does that little light pulse just stay perfectly bright forever? Even in the purest glass imaginable, what happens after it travels across an entire continent? The truth is, it doesn't. It gets weaker. There's a name for this. It's called attenuation, or fiber loss. Over hundreds, and definitely thousands of miles, that super clean signal starts to get dim and fade out. Eventually, the data just becomes unreadable. But the solution they came up with is it's brilliant. Every 40 to 60 miles or so along the cable, the signal passes through what's called an optical amplifier. It's basically a special piece of fiber that gets pumped with its own laser. As our weak signal comes through, it gets re-energized, boosted back up to full strength, and sent on its way. And the best part? It never has to slow down and convert back to electricity. It's a direct power-up for the light itself. And if you want to send even more data, which of course we do, engineers do something incredible. They send dozens of different signals down the exact same fiber at the exact same time just by using different colors of light. Each color, or wavelength, is its own private channel. It's like taking a single-lane country road and turning it into a massive, multicolored superhighway for data. All right, our little pixel has made it. It has crossed oceans, it's been boosted and amplified, it's traveled alongside billions of other bits in different colors. Now for the grand finale. How does it turn from a tiny flash of light back into something your screen can actually show you? This right here is the finish line. At the receiving end of the cable, the light pulse slams into a photodetector, and this little device does the exact opposite job of the laser we started with. It catches those incoming flashes of light and, in an instant, turns them back into a clean electrical signal, the ones and zeros your computer totally understands. And just like that, the journey is over. In a tiny fraction of a second, our one little pixel has gone from electricity to light, traveled thousands of miles, and turned back into electricity just in time to show up on your screen. And remember, this happens millions upon millions of times every single second for every device on the internet. It's just mind-blowing. So let's just boil it all down real quick. The whole incredible system relies on just 4 key ideas. First, we trap light in glass using total internal reflection. Second, we use lasers and modulators to turn our digital ones and zeros into light pulses. Third, we use optical amplifiers to keep that signal strong over those insane distances. And finally, we use photodetectors to catch the light and turn it back into data. That's the whole magic trick. This amazing dance of physics and engineering is what literally powers our entire modern world. So the next time you're streaming something, just take a second to think about the incredible journey those pixels are taking to get to you. And it makes you wonder, now that we've managed to harness the speed of light to connect our planet, what's the next frontier?